Mechanical energy is the sum of an object's kinetic and potential energies, reflecting its motion and position within a system. Let's explore simple instances that showcase the presence of mechanical energy in our surroundings. Hammer. A hammer's mechanical energy drives a nail into the wall by transferring its combined kinetic and potential energy to the nail. Dart gun. The mechanical energy stored in the spring of a dart gun propels the dart forward when released, converting potential energy into kinetic energy. Dumbbell. The dumbbell's mechanical energy is demonstrated when lifted above the floor, storing potential energy that can later be converted into kinetic energy when dropped. Bow and arrow. The mechanical energy of an arrow is converted from the potential energy stored in a stretched bowstring to kinetic energy as it is released, propelling the arrow forward. Bicycle. The mechanical energy of a moving bicycle is derived from the kinetic energy of its rotating wheels and pedals, as well as the potential energy contributed by the cyclist's muscular effort. Athlete. The mechanical energy of an athlete running in a race is a combination of the kinetic energy generated by their movements and the potential energy stored in their muscles, ready to be converted into kinetic energy. Hydropower. In a hydroelectric power plant, the mechanical energy is harnessed from the flowing water. The gravitational potential energy of the water is converted into kinetic energy, which is used to rotate the turbine blades and generate electricity. Wrecking ball. The mechanical energy of a wrecking ball is used to demolish a building as the ball's swinging motion converts its potential energy into kinetic energy, imparting a powerful force upon impact. Bowling. The mechanical energy of a bowling ball is transferred to the bowling pin upon collision, causing displacement and demonstrating the conversion of potential energy into kinetic energy. Windmill. The kinetic energy of the moving wind is captured by the blades of a windmill, which convert it into mechanical energy to perform useful work. Car. The mechanical energy of a car in motion on a highway is a result of the conversion of chemical potential energy stored in its fuel into kinetic energy, propelling the vehicle forward. Cricket. The mechanical energy of a cricket ball is evident as it soars through the air, a combination of the potential energy stored in the bowler's arm and the kinetic energy gained during its release. Electric motor. An electric motor harnesses electrical energy and converts it into mechanical energy, allowing the motor's rotating components to drive the operation of various devices and machinery. Moon. The mechanical energy of the moon is a result of its gravitational interaction with the Earth, which drives its orbital motion and maintains a continuous cycle of kinetic and potential energy. So we've covered sufficient examples to understand mechanical energy. Now let's explore the equation and solve some practice problems. The mechanical energy equation, E mechanical equals half mv square plus mgh, combines kinetic energy, which is half mv square, and potential energy, mgh, where E mechanical represents mechanical energy, m represents mass, v is velocity, g is gravitational acceleration, and h is height. This equation helps calculate how much mechanical energy an object has, considering both its motion and height. Let's try some examples to understand how this equation works. Determine the mechanical energy of a 15 kilograms rock situated on the edge of a cliff at a height of 30 meters. Consider the gravitational acceleration as g is equal to 9.81 meters per second square. Write down the given information, plug in the values into the formula, and find the mechanical energy as requested. We have to determine mechanical energy, so E mechanical is equal to question mark. The mass of the rock is given as m equals 15 kilograms, and the height is given as h equals 30 meter. The rock is at rest, so we can assume velocity as 0 meter per second, and the value of gravitational acceleration is given as g equals 9.81 meter per second square. Insert these values into the equation E mechanical equals half mv square plus mgh. Therefore, the calculation for E mechanical becomes 0 for the first part, as velocity is 0 meter per second, plus 15 multiplied by 9.81 multiplied by 30. So, E mechanical equals 15 multiplied by 9.81 multiplied by 30, and solve this so we get E mechanical as 4,414.5 joule. Therefore, the mechanical energy of the rock is 4,414.5 joule. Let's take one more practice problem. A cyclist with a mass of 70 kilograms is riding downhill from a height of 50 meter with a velocity of 15 meter per second. Calculate the mechanical energy of the cyclist. Use the gravitational acceleration g as 9.81 meter per second square. Write down the given data, plug in the values into the formula, and calculate the mechanical energy as needed. The mass of a cyclist is given as m is equal to 70 kilograms, and the height is given as h equals 50 meter. Also, the velocity is given as v is equal to 15 meter per second. The mechanical energy, E mechanical, is equal to question mark, and the value of gravitational acceleration is given as g is equal to 9.81 meter per second square. Place the given values into the equation E mechanical equals half times mv square plus mgh. So the value of E mechanical becomes half multiplied by 70 multiplied by 15 square plus 70 multiplied by 9.81 multiplied by 50. The value of E mechanical further becomes 7,875 plus 34,335, and finally, we will get the value of E mechanical as 42,210 joule. Hence, the mechanical energy of the cyclist is 42,210 joule. So that's a wrap on mechanical energy. If you found this quick breakdown helpful, show your support with a like, share the video, and hit that subscribe button for future videos.